Designing a Rayleigh step bearing. The question is as follows. Design a Rayleigh step bearing for an application of your choosing, discussing and rationalizing optimal fluid selection, slipper dimensions, and pressure distribution. Firstly, what is a bearing? A bearing is a machine element that constrains relative motion to only the desired motion and reduces friction between moving parts. The design of the bearing may provide for free linear movement of the moving part or for free rotation around a fixed axis. Common uses of bearings include bicycle wheels, machinery which require rotary motion, for example lathes or drilling machines, and computer parts such as CPU fans, floppy disks and hard drive disks. There are multiple types of bearings, some of which include plain bearings, rotary element bearings, so a ball bearing would be an example of that, fluid bearings, or the Rayleigh step bearing is an example of this, and magnetic bearings. The Rayleigh step bearing is known as a bearing with the highest load capacity among all other possible bearing geometries. Discovered by Lord Rayleigh in 1918, he developed a method of introducing a fixed variation of film thickness without the use of tilting. The bearing consists of two parallel surfaces, with one of the surfaces containing a step so that the thickness of the lubricant is varied. This splits the bearing into two zones. One of the surfaces moves relative to the other with velocity u, as shown in the diagram, and due to its geometry, a pressure profile occurs when the surfaces move in this manner, which gives it the ability to support a load. So some assumptions we will make are: the system operates under steady state conditions, the pressures on either side of the bearing are equal to one another, the surfaces are rigid, the width of the bearing is much greater than its length, the fluid used for lubrication has constant viscosity and constant density, and friction between the surfaces and the lubricant is negligible. So as you can see in the diagram, the bearing is split into two sections here, so we're going to call this section zone 1 and this section zone 2. And so the length of the line A to B is going to be called L1, and the length of the line B to C is going to be L2. So H1 and H2 are the distances between the upper and lower surfaces in zone 1 and 2. So H1 is this distance right here, and H2 is this distance here. U is the velocity of the lower surface, so the lower surface relative to the top surface will move in this direction with velocity u. So A is the point at the outside of zone 1, which is this point here. B is the point between zone 1 and zone 2, so it's the point at which the step occurs. And C is the point outside the bearing on the right hand side. So the graph to the side here shows the pressure distribution across the length of the bearing. So this is point A here, and as you can see, as we approach point B where the step occurs, the pressure is constantly increasing, and once we pass point B, so go from B to C, the pressure will decrease. So we've assumed that PA and PC are equal, so that's why we can just set these as equal to 0, and we can just solve for the difference in pressure between point B and these 2 points. So to solve this problem, we're going to use the 1D Reynolds equation, which is this equation here as follows. And through double integrating of this equation with respect to x, we get this formula. So P of x is equal to 6 multiplied by the viscosity of the fluid multiplied by the velocity of the lower surface multiplied by this integral plus C1 multiplied by this integral plus C2. So as I've mentioned, this symbol here is the viscosity of the lubricant, and C1 and C2 are integration constants derived from this equation here. The boundary conditions can be expressed as follows. So P at x is equal to A, or PA, is equal to P at x is equal to C, which are both equal to 0. So employing these boundary conditions, the integration constants become C1 is equal to this here, which is equal to minus 6 by the viscosity by the velocity multiplied by, all in brackets, L1 over H1 squared plus L2 over H2 squared, and all this is going to be over L1 over H1 cubed plus L2 over H2 cubed, and C2 is equal to 0. Using this surface profile, the pressure in the zones 1 and 2 can be described as follows. So when x is between A and B, the pressure will be equal to this formula here, and when it's between B and C, it's going to be equal to this formula here. Since we know that max pressure occurs when X is equal to B, and PA and PC are equal to 0, all we need to do is find PB, and then we can create the pressure distribution curve of the bearing. So bearing dimensions and application. For the application, I've decided that the bearing will support a CPU fan. So fluid bearings are commonly used in computer hardware as they have near silent operation and have a high life expectancy, and they're also well suited to high rotational speeds, which is necessary for a CPU fan. So the dimensions I've decided are the following, and they were chosen based off the typical CPU fan dimensions and rotational speeds found online. So I've chosen a fan that will be 60 millimeters in diameter. I've chosen a 25,000 RPM rotational speed, and it's common to see fans with rotational speeds up to 38,000 RPM. So this isn't too unrealistic. And I'll also assume that the bearing system is 20 millimeters in diameter. So the bearing design will be a bit like the following. Shown aside from directly above is the surface on which the bearing pads are placed. These pads are rigid and do not move or rotate. This is placed above the other flat surface with the fluid bar in between the two surfaces, and the shaft to support the fan is shown in red on the diagram. So what I've just indicated here is that so the other surface will be this will be resting on top of the other surface, and relative to this surface here, the other surface will be moving in this direction. So the fluid as well. So it's going to pass over the landing first and over the step, and that's where the pressure is being generated, and that's what's causing the support. And also the shaft is shown here. So this is what the fan is going to be attached to. So here I've just included another diagram of how the bearing will work. So it will have the lower surface here, the fluid layer in between, and the upper surface, and the bearing pads are going to be on this upper surface. And when the upper surface rotates, it's going to cause a pressure profile in between the lower surface and the bearing pads. And then the shaft, as you can see here, that's what the fan is going to be attached to. So when there is no change in pressure between point A and point B, then from literature it's found that the optimal dimensions for the Rayleigh step bearing are the following. So the ratio between H1 and H2 should be 1.866, and the ratio between L2 and L1 is going to be 2.55. So if we assume that H1 is equal to 1 millimeter and L1 is equal to 5 millimeters, then we get the following values. So H1 is equal to 1 millimeter, H2 is equal to 1.866 millimeters, L1 is equal to 5 millimeters, L2 is equal to 12.75 millimeters. So the next thing we need to do is work out the velocity u of the lower surface that we were talking about earlier. And then we can do this is we use the rotational speed of the fan, and if we use this formula here, that's going to be the angular velocity is equal to the size of the angle travelled over a given time. So first we need to work out the angular velocity, and the size of the angle is going to be equal to 25,000 multiplied by 2 pi radians, and that's per minute, so over 60 seconds, and we get an angular velocity of 2,618 radians per second. And then we can use this to work out u by using this formula here. So the velocity is equal to the radius multiplied by the angular velocity, and this is the velocity on the outside of the bearing system as I've shown earlier. So the radius, since the diameter of the bearing system is 20 millimeters, that's going to be equal to the radius is going to be equal to 10 millimeters, which is 0.01 meters, and you multiply that by the angular velocity, and that is going to give you 26.2 meters per second. That's the velocity of the lower surface. So for the type of lubricant, I chose sewing machine oil, as it is commonly used to lubricate CPU fans. And this specific one, Maxilene sewing machine SMO 21060, at 40 degrees Celsius, it has a viscosity of 15 millimeters squared per second, or 0.015 Pascal seconds, and that was found online. So now we can move on to the final calculation, and so far we have H1 is equal to 0.001 meters, H2 is equal to 0.001866 meters, L1 is equal to 0.005 meters, L2 is equal to 0.01275 meters. The velocity of the lower surface u is equal to 26.2 meters per second, and the viscosity of the sewing machine oil is equal to 0.015 Pascal seconds. And from this we can work out that A is equal to 0, B is equal to L1, which is 0.0005 meters, and C is equal to 0.01775 meters. So now if we sub in values to the first formula we derived earlier on, the pressure when x is between A and B, we'll get something that looks like the following, and that is equal to 11790 minus 8528.98, which is equal to around 3261 pascals. So now we've worked out PB, which is the max pressure between points A and C. So the weight W a bearing is capable of supporting is equal to the area of the triangle made by the pressure distribution curve and the x-axis. So we can figure out the area by using this formula. It's just equal to half the base by the height. So what I've done is I've multiplied 0.5 by, this is the base of the first triangle, multiplied by the height, which is PB, plus 0.5 by the base of the second triangle, multiplied by PB. And when you sub that in, you get 28.94 newtons. And since the system we have created has two bearing pads, that particular system would be capable of supporting a load twice this value, which is equal to 57.88 newtons. So finally, to summarise, we will just go through what we've worked out. So the question said, design a Rayleigh step bearing for an application of your choosing, discussing and rationalising optimal fluid selection, slipper dimensions and pressure distribution. So optimal fluid selection, we chose the sewing machine oil. The slipper dimensions, as we have H1 is equal to 1 millimeter, H2 is equal to 1.866 millimeters, L1 is equal to 5 millimeters, and L2 is equal to 12.75 millimeters. And for the pressure distribution, we know that the pressure is going to be equal to 0 at PA and PC, and the max pressure is going to be 3261 pascals.